Very good. Okay, thank you guys very much for coming back for part 2. We did all of the hard work. Now it's time for the payoff when we apply it to quantum mechanics. Carlos and Danupa, can you guys hear and see everything okay?
Yeah.
Okay, great. So the thing that we just finished deriving was the expression for the Hamiltonian and the momentum operator reduced down in terms of these objects that will become shortly creation and annihilation operators. So that the Hamiltonian is counting the energy of individual photons, h bar omega. The momentum is counting the momentum of individual photons, h bar k. The creation and annihilation operators are constructed out of non-trivial combinations of the fields in momentum space. So these guys were a Fourier transform over position to momentum. There's some prefactor, and it's a combination of the field itself and its canonical momentum. So now we can proceed with canonical quantization. The canonical quantization procedure works exactly the same way here that it did for us last semester. So canonical quantization. So we will start off by identifying the Poisson brackets of the quantities here in these expressions, and then we will promote them to commutators, and we will promote them to operators. So we started off with the canonical algebra of the field and its own momentum. So we had a Poisson bracket of component AI of position R and T with component AJ of some other position R prime and T was equal to 0. A with A is always 0. Likewise, pi with pi is always 0. The only one that's non-zero is the coordinate with its own correctly paired momentum. So AI pi j of R and R prime at equal time was delta ij, so you've got to be talking about the same component, three-dimensional delta function of R minus R prime. So you've got to be talking about the field at the same point. So now we want to use these commutation relations to derive what the commutation relations are for A and A dash. So based on this decomposition, let me now plug in, let's say, let me calculate the one that's non-trivial. So we'll show that A with A is 0, A star with A star is 0. The only one that's non-zero is A with A star. So let's work that one. So if I calculate the Poisson bracket of AK, let's say component I, with AK prime with component J. So each A and A star is A star. Each A and A star is a position integral. So I've got integral D3R, integral D3R prime. I've got the Fourier factors. I have e to the minus I k dot R, e to the plus I k prime dot R prime. I have the overall factors. So I've got square root omega over 2 pi h bar squared, 2 pi c squared h bar. I have another omega prime over 2 pi c squared h bar. And now the business end of this is the Poisson bracket of the combination of A's and pi's. So this is a Poisson bracket of 1/2 AI of R and C plus, let's say, pi I c divided by k, pi sub I of R and C. Poisson bracket with 1/2 A sub j of R prime and C minus 2 pi I c over k, pi sub j of R prime and C. So the integrals and all the extra factors just hang around, and I'm really just calculating the Poisson bracket of A plus pi with A minus pi. Since the bracket of A with A is 0, I don't even care about those terms. Likewise, the Poisson bracket of pi with pi is 0. The only thing that I need to keep from this bracket are the cross terms. 1A with 1 pi and the other pi with the other a. So that gives me exactly two terms that contribute. So that Poisson bracket, 1/2 ai of r and t plus 2 pi I c divided by k pi sub I of r and t with 1/2 a sub j of r prime and t minus 2 pi I c over k prime. Sorry, I guess this should have been k prime. Pi sub j of r prime and t. The only ones that are non-zero are the cross terms. So the cross terms are, let's see, this a and that pi gives me minus I pi c over k prime. Poisson bracket of ai of r and t with pi j of r prime and t. The other cross term is this one with that one, which is plus I pi c divided by k, Poisson bracket of pi sub I of r and t with a sub j of r prime and t. Yes. So then I plug in the canonical algebra of these guys. So this is delta ij, delta 3 of r minus r prime. Same for this one, but with a minus sign because they're in the wrong word. Negative delta ij, delta 3 of r minus r prime. So when I do that, these terms become almost equal. So I get minus I pi over k prime minus I c over k prime minus I pi c over k delta ij delta 3 of r minus r prime. So now we've evaluated the Poisson bracket. I plug it back in, and just like before, I have two integrals, r and r prime, and I've got a delta function. The delta function is going to kill the integrals down to 1. So what I get when I plug it back in and I utilize that delta function, Poisson bracket of a sub k component I with a sub k prime star component j is we've got a delta ij that's hanging out up front. I've got one integral that's left because I killed the d3r prime integral. d3r, now I have e to the minus I k minus k prime dot r. Still have these square roots hanging out, 2 pi c squared h bar under omega, 2 pi c squared h bar under omega prime, times what's left from this, which is just minus I pi, and I'm going to call this c squared over omega prime, because k is omega over c. Minus I pi c squared over omega. So finally, everything finishes simplifying. The position integral only covers that Fourier phase. So this gives me another delta function, 2 pi cubed, delta 3 of k minus k prime. So since k is now equal to k prime, these annoying factors are now equal to each other, and everything fully simplifies. So I get 2 pi cubed, delta ij, delta 3 of k minus k prime, and then the remaining factors are omega over 2 pi c squared h bar times minus 2 pi I c squared over omega. Most everything simplifies. The 2 pi goes, c squared, omega, and I'm left with just minus I over h bar. So at the end of the day, what I get for this Poisson bracket is minus I over h bar 2 pi cubed delta ij delta 3 of k minus k prime. The other Poisson brackets of A with A and A star with A star are all zero. The reason is exactly the same thing. When I take just the cross terms, A with A will have a plus and a plus, or a minus and a minus for A star and A star. And that means one of the brackets is in the wrong order. So these guys will then come in with a relative sign between. You'll have negative and positive. And then at the end of the day, when I get a delta function, those things are going to cancel out. So I get 0. So what this gives me is exactly the algebra that we want for the creation and annihilation operators. If I translate this I and j components into lambda and lambda prime, then this tells me that the Poisson bracket of ak lambda with ak prime lambda prime is 0. Poisson bracket of a star k lambda with a star k prime lambda prime is also 0. The only one that's non-zero is this one, Poisson bracket of ak lambda, ak prime lambda prime star is minus I over h bar 2 pi cubed delta 3 of k minus k prime delta lambda lambda prime. So this is exactly what we want. And now we're ready to quantize it by using canonical quantization. So the procedure is to take all Poisson brackets like the one that we had between x and p. X and p are canonical variables whose Poisson bracket is 1. To turn that into quantum mechanics, we make x an operator, p an operator, the bracket becomes a commutator, and the commutator has a factor of I h bar. So this tells me that my creation and annihilation operators will be commutator of a k lambda, a k prime lambda prime is 0, they commute. Commutator of a dagger k lambda with a dagger k prime lambda prime is 0, they commute. And commutator of a k lambda with a dagger k prime lambda prime is the minus I over h bar is exactly canceled by the I h bar from the canonical quantization procedure. And I just get 2 pi cubed delta 3 of k minus k prime delta lambda lambda prime. When I quantize, I also have to quantize the Hamiltonian and momentum operators. So we said the Hamiltonian before quantization was sum over lambda integral d3k over 2 pi cubed h bar omega ak lambda star ak lambda. Now when we quantize this to make the Hamiltonian operator, I'll put hats on them, but I have to remember that the order is ambiguous in classical mechanics. So the standard prescription is to symmetrize this when you quantize it. So we'll write this as 1/2 a star a plus a star. So we get both orders. So when I do this, I get sum over lambda integral d3k over 2 pi cubed h bar omega, and now I have 1/2 ak lambda dagger ak lambda plus ak lambda dagger. So this is almost what I want. I've got to rearrange the order. So let me add and subtract this piece to write this as a commutator. So this is sum over lambda integral d3k over 2 pi cubed h bar omega. I get 2 of these factors, which cancels the 1/2 ak lambda dagger ak lambda plus 1/2 the commutator of ak lambda dagger. So this is exactly the Hamiltonian that I want. But something really funny happens in quantum mechanics when I promote these things to operators. There's an extra constant. So this constant looks like the plus 1/2 h bar omega that comes from the 0-point energy of the harmonic oscillator. Every harmonic oscillator has a minimum energy at n equals 0 of 1/2 h bar omega. My quantum field is made up of an infinite superposition of harmonic oscillators. So there's an infinite set of 1/2 h bar omegas that are hanging out as the 0-point energy of the quantum field. So that shows up because of this 1/2. There's an integral here, and even worse, when you plug in this commutator, this actually has delta of 0. So in a couple of different ways, this constant is infinity. So this is something that is very peculiar about the quantization of the field. The vacuum, the state that has no photons in it, has infinite energy. But somehow in particle physics and quantum mechanics, none of that matters. This is just a constant. So we get Hamiltonian equals sum over polarizations, integral over momenta, h bar omega, ak lambda dagger, ak lambda, plus a constant. And it just so happens that that constant is ridiculously infinite. So what we do is we say, I don't care about the constant. I define the Hamiltonian to be 0 when this thing is 0. So you subtract off the constant. That works okay in quantum mechanics, but we're really just sweeping this weird infinity under the rug and hoping it doesn't come back to bite us. For particle physics, that's fine. E&M doesn't care about the absolute 0 of the energy. It only cares about relative excitations of the energy compared to the vacuum. All of the other physics that we actually observe with creating particles doesn't care about that. There is one force in nature that does, however, and that is gravity. Gravity cares about the total energy of the vacuum. So shoving this under the rug for now is okay. It doesn't cause a problem in quantum theories, but it poses a very deep problem for quantum gravity. When you try to take this framework and include gravity in it, you end up with a vacuum energy, which looks like a cosmological constant that is ridiculously large. It is 120 orders of magnitude larger than the current limit on the cosmological constant experiment. So this is an indication of a very deep problem when it comes to quantum gravity. For quantum gravity, you get a gravitational force i.e. the cosmological constant which is 120 orders of magnitude too large. So there's some kind of very deep problem here of quantum gravity and how gravity can play nicely with quantum field theory in general. Deep unresolved problem for quantum gravity. However, for particle physics, the 0 of the energy is absolutely arbitrary. Nothing else depends on that, and we can just forget about the constant. So if we sweep that infinite constant under the rug, then we nicely have that the Hamiltonian for the excitations is the sum over polarizations, integral over momenta, 2 pi cubed, h bar omega, ak lambda dagger, a k lambda. And in exactly the same way we get for the total momentum, P as an operator is sum over polarizations, integral over momenta, h bar k, a k lambda dagger, a k lambda. In principle, the same kind of infinite constant starts to show up here for the momentum, but it actually cancels itself because the integrand is odd under k goes to negative k, and so that infinite constant gets canceled. I don't know if that's better or worse than saying I have an infinite constant, but I don't care. Okay, having quantized the creation and annihilation operators, having their commutation algebra, and knowing how that affects the energy and momentum tells us everything we need to know about the allowed states of the system. So the first state that one can define is the vacuum state. This Hamiltonian has a ground state. That's very important. It would be a very deep problem, and this would not be a useful theory for particle physics if this Hamiltonian didn't have a minimum energy. But we know that A dagger A does have a minimum energy, that all the harmonic oscillators can be sitting in their lowest energy states. So we call the ground state of the quantum field the vacuum. So that state will denote by 0. This is the quantum state that has no photons in it, so it cannot be lowered further. So it cannot be lowered further. The annihilation operator, AK lambda, acting on the vacuum state 0, must be 0 for any momentum or any polarization. For all K and lambda. So this is the vacuum of photons. Now, once I have the vacuum, now I can define the particle states. An excitation of the vacuum is what I get when the creation operator acts on it. So let me define the state K lambda is defined to be what I get if I take the creation operator A dagger of K lambda and act on the vacuum with it. The claim is that this state that I get by creating an excitation on the vacuum is an eigenstate of energy and an eigenstate of momentum with exactly the eigenvalues you think it should have. Eigenstates of H and of P. So what do I get when I take the Hamiltonian and I act on that state K lambda? This is by definition the Hamiltonian acting on the state Hamiltonian times the operator A K lambda dagger times the vacuum. I can relate this to the algebra of the creation and annihilation operator. So I can reverse the order of this. This is A K lambda dagger Hamiltonian acting on the vacuum, plus the commutator of Hamiltonian with A dagger K lambda acting on the vacuum. The vacuum state is the state with no energy, right? So another way to say this is if I take the Hamiltonian operator and I evaluate it on the vacuum, by the definition of what I mean by the vacuum, I immediately get 0. So if I take Hamiltonian acting on the vacuum, the Hamiltonian is sum over polarizations, integral over momenta, H bar omega, A K lambda dagger, A K lambda. And now this is acting on the vacuum 0. But the vacuum goes to 0 as soon as it's hit by any annihilation operator. 0. So just like you expect, the vacuum is defined to have 0 energy. And for the same reason, the vacuum has 0 momentum. Now, what about this excited state? To get that, I need to evaluate the commutator of the Hamiltonian with the creation operator. The commutator of the Hamiltonian with the creation operator, A K lambda dagger, is sum over polarizations, let me call it lambda prime. Integral over momenta, let me call them K prime. 2 pi cubed, H bar omega prime, and then the operator part is A dagger, K prime lambda prime, A K prime lambda prime. That's the operator coming from the Hamiltonian, and I'm taking its commutator with A, K lambda. There. So I open up the brackets. This thing is equal to commutator of A, K prime lambda prime dagger with A, K lambda dagger times A, K prime lambda prime plus the other order. A, K prime lambda prime dagger, A, K prime lambda prime, A, K lambda dagger. The commutation algebra tells me that A dagger with A dagger is 0. A with A dagger, however, is not. This one gives me 2 pi cubed delta function of K minus K prime delta lambda lambda prime. So when I plug this in, this gives me sum over lambda prime integral d3 K prime over 2 pi cubed h bar omega prime, and what I'm left with is A K prime lambda prime dagger times 2 pi cubed delta of K minus K prime delta lambda lambda prime. And everything is exactly set up so that 2 pi cubed cancels the 2 pi cubed. Delta function cancels the integral and sets K prime equal to K. The Kronecker delta cancels the sum over lambdas. And I get exactly plus h bar omega A K lambda dagger. This is the algebra of what the raising and lowering operators are supposed to do. It's exactly this way before for the harmonic oscillator itself. So in the same way, we have commutator of the Hamiltonian with AK lambda dagger is plus energy h bar omega AK lambda dagger. Commutator of the Hamiltonian with AK lambda, the annihilation operator, is minus h bar omega AK lambda. Same thing for the momentum operator. P with AK lambda dagger is plus h bar k AK lambda dagger. P with AK lambda is minus h bar k AK lambda itself. So this is telling me that A and A dagger act like creation and annihilation operators like they're supposed to. They add energy h bar omega and momentum h bar k, or they subtract it, depending on the case. So going back to my state K lambda, which is defined to be A K lambda dagger acting on the dagger, this thing is an eigenstate of the Hamiltonian. H on K lambda is Hamiltonian A K lambda dagger on the vacuum, which is A K lambda dagger Hamiltonian on the vacuum plus the commutator. Acting on the vacuum. The first term is 0, and this second term is plus h bar omega AK lambda dagger. So this is h bar omega, and AK lambda dagger acting on the vacuum is exactly my single particle state, K lambda. So the energy of the state, which I get by letting the creation operator act on the vacuum, is exactly h bar omega. I've added one quantum of energy to the field. In exactly the same way, the momentum operator acting on the state K lambda, because it has the same commutation algebra, is h bar k times the same state value. So that means that this state, the one that I get by letting the creation operator act on the vacuum, is the single particle state. This contains a single photon with energy h bar omega, momentum h bar k, and polarization epsilon sub lambda. So this is how you get particles out of the field theory. The particles are the discretized or quantized excitations of the field. And because they are harmonic oscillators for each momentum state, they add exactly one quantum of energy and momentum every time. Now let's come back to that question about the polarization, because this has physical bearing on the amount of angular momentum that the photon carries. We saw that the photon must be transversely polarized. So we saw that the polarization vector must be perpendicular to the momentum of the photon. This is peculiar because the photon is a spin-one particle. It's a vector field. Right? So A of R and Z is a three-component vector field. And we know from our angular momentum decompositions that a three-component vector corresponds to a spin-one operator. That when I make this thing an operator, let's say A sub K, that I can break it up into spherical components. So I can talk about the L equals 1, M equals plus 1 combination of components, which is exactly negative 1 over root 2 AX plus I AY. I can talk about the L equals 1, M equals 0 component, which is just AZ. And I can talk about the L equals 1, M equals minus 1 component, which is plus 1 over root 2 AX minus I AY. So my vector field is supposed to have three states in it, but it doesn't. This transversality constraint forbids one of these states. So for example, if the momentum is taken to be along the z-axis, if K is along z, then that means that my K dot A must be equal to 0 is telling me that AZ must be equal to 0. So this transversality constraint is actually telling me that this state, which carries 0 projection of angular momentum along the momentum direction, is forbidden. If this state existed, then your photon would not satisfy Gauss's law. So, in a very strange way, even though the photon is a spin-one particle, it only has 2 allowed spin states. The spin is either up or down, and it cannot be 0 because of this condition. So this z direction is really talking about the direction of the angular momentum, the direction of the photon momentum. So that means that there are exactly 2 polarizations allowed for the photon. 2 polarizations corresponding to 2 different values of the angular momentum. I can have what you might call a right-handed photon, which is sort of rotating circularly like this. The momentum is going along this direction. And the polarization must be rotating in a right-handed way. So that's this projection, which means that the spin, or the angular momentum, is pointing along this axis, LZ equals plus 1. Or I can have the opposite polarization. You might call it a left-handed circular polarization, where the momentum is going in one direction, but the spin is pointed in the opposite direction. LZ equals minus 1. So these are referred to as helicity states. So the statement is the photon spin must point along its momentum direction. So there's always plus 1 unit of angular momentum or minus 1. never LZ into zero. So this is a peculiar feature of the fact that this is a massless particle, the fact that it's always traveling at the speed of light. That means if the spin is forward and this thing is moving in the speed of light, you can never run fast enough to get in front of the photon, where it looks like the momentum is going in the opposite direction. So it's a peculiar consequence of the fact that the photon is exactly massless and travels at exactly the speed of light. So these are the single photons and their properties. The virtue of quantum field theory is that it gives you a framework to describe multi-particle states. Multi-particle states are built in exactly the same way. So I can define a two-photon state, A K1 lambda 1 dagger, acting on A K2 lambda 2 dagger, acting on the dagger. Let's call that state the two-photon state K1 lambda 1 K2 lambda 2. This now is an eigenstate of the Hamiltonian. K1 lambda 1 K2 lambda 2. Whose energy is h bar omega 1 plus h bar omega 2. And it is an eigenstate of the total momentum operator. K1 lambda 1, K2 lambda 2 equals h bar K1 plus h bar K2. So not only does it have the properties that you expect, the commutator algebra of A dagger with A dagger determines the particle statistics. Since A dagger commutes with every other A dagger K1 lambda 1, A dagger K2 lambda 2 is equal to 0, that tells us that this two-photon state is automatically symmetric. So that means that my state K1 lambda 1, K2 lambda 2, which is AK1 lambda 1 dagger, AK2 lambda 2 dagger acting on the dagger. These guys commute, so I can swap the order. AK2 lambda 2 dagger, AK1 lambda 1 dagger. This is the same state, but with the photons reversed. K2 lambda 2, K1 lambda 1. So because of this algebra, it is automatically symmetric. Under particle exchange. So the theory itself tells us that photons must be bosons. The bosons are synonymous with the fact that their creation operators commute with one another. If you want to make fermions, you can't do it with commutation. You have to quantize it a very different way that involves anti-commutators. So that is associated with problems where the Hamiltonian isn't well defined if you try to do it with a commutator. And so instead you have to quantize with an anti-commutator. That gives you fermions instead. Okay, this is the entire structure of the theory. This describes how to populate the quantum vacuum with any number of photons that you want. It doesn't tell you anything about how they interact. The interaction of the electromagnetic field requires you to put in the rest of the electromagnetic Hamiltonian. Right, so this Lagrangian and the quantization that we used for it, so 1 over 8 pi integral d3r e squared minus b squared. I think if I'm talking about the Lagrangian density, I don't want to integrate it. This describes the free electromagnetic field. Which are the photons. We already described earlier in the semester how to do the coupling of the electromagnetic field to charge distribution. So we did it by minimal coupling. If we had p squared over 2m for a free particle, when you charge it under minimal coupling, then this becomes p minus q over ca squared over 2m. And so this leads to an interaction Hamiltonian. Now, my electromagnetic field can be an operator, described exactly as we've done here. So then you get an interaction which relates minus q over 2mc, the momentum of the particle that has a charge, to the electromagnetic field, which is also an operator. This lets us go beyond the treatment that we did earlier in this semester, where the electromagnetic field was an external spectator. Just a constant external field before. Now, it is a dynamical quantum object. Dynamical quantum operator. And this means if you take this Hamiltonian with the states that are described by this Lagrangian for the photon field, then you can describe things like the spontaneous decay of excited states of hydrogen. So you can do something like starting off with the hydrogen atom in, let's say, the n equals 2, L equals 1 state. And you can calculate its decay rates into the ground state, n equals 1, L equals 0, plus a photon with energy h bar omega and momentum h bar k. So this coupling where you turn on both the description of the electromagnetic field as a living quantum object and the description of the electron in the atom can be used to calculate the lifetime. So you do exactly the same kind of Fermi's golden rule calculation that we did before. You calculate the transition rates, and then you use that to calculate the lifetime. So this can be used to calculate the lifetime of excited states due to spontaneous emission. That's just the most elementary application of the quantum field theory. That's what happens if the electron is a separate object that has fixed particle number, but the photon field is allowed to fluctuate. If you really want to bring this into its full glory, then you need to introduce a quantum field for the electrons as well. That describes the creation of particle-antiparticle pairs. So that allows fluctuations in the number of electrons, meaning matter-antimatter pair production. With two quantum fields, the electromagnetic field and the electron field, you get the complete theory of quantum electrodynamics. Or QED. QED has two elementary interactions, one of which describes the electron emitting or absorbing a photon with energy h bar omega and momentum h bar k, exactly as we described. And it also allows for the production of electron-positron pairs, where you now have a quantum of the electromagnetic field, the photon, which then pair produces an electron and a positron. Quantum electrodynamics is the single most successful theory ever created by man. This has been tested to unbelievable degrees of precision. The muon G-2 experiment just indicated fascinating deviations from the predictions of quantum electrodynamics that may indicate the existence of brand new particles beyond the standard model. So this is, let's say, the most successful, precisely tested theory ever. This is also the basis for all quantum theories that we know. Quantum field theories describe all known quantum particles and their interactions. So if you take this framework of quantum field theory, where you have Lagrangian densities, Hamiltonian densities, you have creation and annihilation operators for all the different polarizations, this framework, together with a description of what are the interactions of the particles, which you can completely enumerate based on the symmetry of their gauge. This describes everything that we know about quantum physics. This is U1 gauge symmetry, which is electromagnetism. The interactions corresponding to SU2 are the weak nuclear force. So this leads to a theory with W and Z bosons, neutrinos, etc. And SU3 leads to the strong nuclear force. This is quarks and gluons, which ultimately lead to their bound states into protons, neutrons, and nuclei. So this is the framework that sort of brings everything that we learn about classical mechanics and single particle quantum mechanics together into a unified framework. This is, in my opinion, the pinnacle of physics. This is the completion of all of the ideas that we understand about symmetry transformations, classical mechanics, and the quantum properties together with relativity. So quantum field theory is the best theory that we have to understand the truth with a capital T as much as we possibly can. This does not mean that it has solved everything. There are still important questions out there about gravity, quantum gravity, how all of that plays with this. Why are the masses and number of particles in the standard model the way they are? It doesn't explain everything, but quantum field theory is the most complete framework we have for how to approach quantum physics in general. So with that, thank you guys very much for your patience. We've been aiming at something like this all year long, and I hope to see some of you guys next year in quantum field theory, where we will take this entire framework and we will build it from the ground up in a way that is compatible with relativity. And we will explicitly construct quantum electrodynamics and other simple theories, do calculations with it, and hopefully equip you to go on to do the research of your choice. Thank you guys very much. Questions, comments, concerns?
I do have a question.
Thanks very much.
So the fact that infinity constant, the fact that it doesn't work with gravity doesn't mean that, or shouldn't it mean that you shouldn't do that at all with any force, regardless if it's gravity or the electromagnetic one?
It's a good question. There are possible solutions for how that infinity or very large constant could be canceled out, right? So one of the simplest explanations is maybe there are other fields and particles out there in nature we haven't discovered. So some of them come in with a positive constant, some of them come in with a negative constant. It's imaginable that if you had all of the fields in nature, a full description of quantum mechanics, that all of those positive and negative vacuum contributions would conspire to cancel out and give you something consistent with what we observe in nature. Or maybe quantum gravity doesn't interact in the same way, right? Maybe somehow, for some reason we don't understand, quantum gravity actually does not get a correction from the vacuum energy. We don't have a quantum theory of gravity, so we can only guess at how it works. I think it points to a mismatch between how we understand gravity and how we understand quantum mechanics. The fact that this works so precisely well in describing particle physics indicates that it's not completely crazy. But I think that it just goes to show that when you try to bring gravity into the picture, something fundamental has to be added to the theory that goes maybe beyond quantum field theory as a whole. Maybe there's some geometrical, relativistic space-time picture in curved space that we need to include. This is also part of what motivates people to look for string theories. And it's also part of the motivation behind one of the natural explanations would be supersymmetry. So supersymmetry is a large class of theories that does exactly that delicate cancellation that I was talking about. If you take every particle in nature that leads to, say, some large positive vacuum energy, and you double it, and now you imagine for every photon, which is a boson, there is a fermion called a photino, that would bring in exactly a negative contribution to matching. So the idea behind supersymmetry is that you can engineer exactly that cancellation of the vacuum energy if you just double the number of particles in the universe. If that's true, and there's reason to think it might be, we should be able to see them. So part of the exercise is to try and look for supersymmetric particles or something else that could help explain this discrepancy. And maybe, for all we know, maybe those new particles are what's behind the interesting discrepancies in the muon G-2 measurement, or the flavor violation in decays at the LHC. We're seeing now, just in the last couple of months, some really exciting hints of physics beyond the standard model that could indicate new particles. And depending on what kind of particles they are, that could give us a huge clue about whether supersymmetry is the right answer, for instance. That can then explain why the quantum vacuum is not infinitely high energy, and maybe something that is consistent with the cosmological constant we see in astronomy. So it's a good question, and we don't have an answer to it, but if the experiments keep going the way they've been, we might actually have some insight into this in the next few years. Did that answer your question, Carlos?
Yeah, it does. Thank you.
Okay, anything else, guys, before we hang up? All right, thank you very much for coming and hanging out. I hope this was useful and exciting, and I hope to see you guys in field theory next year.
Thank you.
Thank you.
Take care.